Hi, I'm Reid Prichard, and I will be showing you a study on the ability of shark skin to inhibit flow separation. First, why does flow separation matter? Well, flow separation has huge impacts in dollars and in human lives. In airplanes, stalls which are caused by flow separation caused 20% of fatal crashes from 2000 to 2014. Additionally, flow separation limits airfoil design, which reduces fuel efficiency. In the shipping industry, propellers are only about 50% efficient, and shipping emissions have been linked to over 400,000 deaths annually. On top of that, fuel costs are about $100 billion annually. So in just these two industries, there are huge effects in terms of human lives and economic impacts of flow separation. But in general, compromise in all areas is common to avoid flow separation. As with many recent engineering problems, we are turning to biomimicry for inspiration to solve our problems. And in this case, the source is sharks. Sharks are apex predators. They're very agile, very fast, and a lot of this is thanks to structures on their skin called denticles. These denticles grant sharks beneficial fluid dynamical properties. For quite some time, research has focused on these denticles' ability to reduce drag. However, within the past decade or so, it has been observed that these denticles are able to actively mitigate flow separation. When the flow reverses in the boundary layer, this causes the denticles to actively lift or bristle, and their interference with this flow causes the flow to reattach. Experimental studies have been able to quantify this ability to some degree, but insight into the mechanism or any computational studies are lacking. To start out, let's go over the study details. The objective of this study is to study the mechanism of this flow separation controllability using a simplified Coué flow. We use this Coué approximation because it allows an inexpensive exploratory study of the denticle in the viscous sublayer. Turbulent streaks carry a relatively large amount of momentum, so we are approximating them as a wall as shown in the diagram to the right. You can see that there's a scale being bristled. The scale has some length being bristled at some angle. There's a pressure gradient from right to left, and the top boundary is a moving wall which simulates those streaks. Furthermore, this domain has a height of A. We are solving this using ANSYS Fluent in double precision, and as shown in the diagram, this is a 2D geometry. The inlet pressure is 3 millipascals and the outlet pressure is 0 millipascals. As mentioned, the upper wall is a moving boundary with a velocity of u, which will vary from case to case. Because this is within the viscous sublayer, we simply used a laminar viscous model, and you can see our spatial discretization schemes over on the right. Before getting into the results, let's go over some characteristic numbers and other important metrics. As with many studies, the Reynolds number is important, and in this case, it's the channel Reynolds number, where the characteristic length is the height of the domain, and the velocity is the velocity of that upper moving boundary. We control this Reynolds number by varying the density and the viscosity. The next important number is the Lang number, which represents the ratio of the streamwise pressure gradient to the fluid momentum before bristling. We control the Lang number by varying the fluid density. Next, we introduce the novel parameter, the Strasser number, which is defined as 6 divided by the product of the Reynolds number and the Lang number. The Strasser number indicates the directionality of the net mass flow relative to the streak before bristling. So when the Strasser number is less than 1, that indicates a net mass flow in the negative x direction. A Strasser number of exactly 1 indicates a net mass flux of 0, and a Strasser number greater than 1 indicates mass flux in the positive x direction. We control the Strasser number by scaling the domain's physical dimensions and by varying that upper wall velocity. Next, a geometric parameter that's important is the blockage ratio. And the blockage ratio is defined as the length of the denticle times the cosine of its angle divided by the channel height, which essentially comes out to the proportion of that channel's height that's blocked by the bristled denticle. The last important characteristic number is the dimensionless wall distance, or Y+. Our first metric that we are using is mass flow recovery, which we have defined as the simulated mass flow for a certain case minus the mass flow of that case without the denticle divided by the mass flow of a corresponding QA flow with the same U and no pressure gradient. This mass flow recovery indicates the ability of a certain case to return the flow to its non-reversed state. Second, we're considering the peak backflow velocity, which is measured as the minimum x velocity along the midline that originates at the base of the denticle. This backflow velocity is normalized according to the upper wall velocity, and it presents just an alternative metric to quantify this backflow mitigation, sort of a complementary measure to the mass flow recovery. In our design of experiments, we set up two different parameterizations of geometric parameters and these characteristic numbers that I just mentioned. In our first parameterization, we cover 8 different values of the denticle angle and 4 different values of denticle length. Additionally, we cover 19 combinations of the characteristic numbers we mentioned, which are shown below. So you can see that the Reynolds number varies from about, I think, 0.03 to 1. The Lang number goes from nearly 0 to nearly 200. The Strasser number goes from 1/4 to just over 6. And the Y plus goes from just about 0 to 5. In combination with these different geometric parameters, this comes out to 608 permutations for our first parameterization. In our second parameterization, we cover 4 values of denticle angle as opposed to 8, and instead of covering the denticle length, we use the blockage ratio. So instead of using 4 values of denticle length, we use 20 values of blockage ratio. In this, we were primarily concerned with the geometric effects, so we only used one combination of characteristic numbers, where importantly the Strasser number is 1. And in combination, this gives us 80 permutations in our second parameterization. Let's go over validation and grid independence. Because of our QA simplification, we are able to compare our data to an analytical solution. You can see on the right a plot of both an analytical QA velocity profile and our measured velocity profiles at the inlet and the outlet of our domain. You can see that all of those coincide, which demonstrates validation for our data. Additionally, for grid independence, we have the length scale of our mesh, which would quadruple the number of elements. We found that this only changed mass flow recovery by about 1%, which demonstrates an acceptable level of grid independence for our results. And you can see in the bottom our mesh for parameterization A. Moving on to some results, we'll go over the mass flow recovery data for parameterization A. You can see in the plots that Reynolds number, Lang number, and Y plus have no effect on mass flow recovery because the data points for cases 1 through 12 all actually overlap. The top plot and the bottom plot demonstrate the same data. They show the same data. The bottom plot is just zoomed in a little bit. You can see that the Strasser number influences both the slope and the curvature of the relationship between blockage ratio and mass flow recovery. Looking to that bottom plot, you can see that over a Strasser number of about 2.5, which is case 17, any cases with Strasser number higher than that demonstrated a negative effect on mass flow recovery of any blockage that we tested. And intuitively, this makes sense. So if the flow before reversal begins is already biased to the right, bristling a denticle into that flow is just going to obstruct the flow and reduce its flow to the right. Taking a look at the peak backflow velocity for parameterization A, we again see the same trends. So Reynolds number, Lang number, and Y plus have no measurable effect on the backflow velocity because in all cases, those data points for cases 1 through 12 are exactly on top of each other. Again, the blockage tends to have a beneficial effect across the board except for those cases with a larger Strasser number. So again, case 17 is kind of where you see that trend stopping. So cases with a Strasser number less than case 17, a blockage decreases backflow velocity, but for cases 17, 18, and 19, blockage doesn't generally help, and in some cases it actually increases that backflow velocity. To again and further demonstrate the independence of this data from Reynolds number and Lang number, I've shown some contour plots of x velocity on the left and Q criterion, which is the second invariant of the velocity gradient tensor, on the right. In the top, there's case 5 with our lowest Reynolds number of 0.03 and our highest Lang number of 192. And on the bottom, you see case 6, which has the highest Reynolds number of 1 and lowest Lang number of 6. Previously, we showed those macro quantities, kind of insensitive big picture things like velocities along a single line and mass flow that showed their equivalent, but also these more sensitive micro measures agree. So you can see the individual points of the velocity fields have the same pattern looking from top to bottom. There's really no discernible difference in those velocity fields. And on the left, the magnitude of the x velocity appears to be identical between those two cases, as well as the distribution of the Q criterion on the right appears to be identical between the two. So this just further demonstrates that Reynolds number and Lang number have no effect on our results. Now moving on to our second parameterization, which, as previously mentioned, focuses a little bit more on geometric effects. So we were hoping, among other things, to capture the optimum blockage ratio for mass flow recovery. And you can see on the top plot that we found that, and it's right around 0.7 depending on the angle. So as blockage, as Denikel angle decreases, so does that optimum blockage ratio, but all cases tested are right around 0.7. We should note that this Coué approximation the approximation breaks down as blockage number increases, because physically that represents a Denikel that's getting closer and closer to a streak, so the assumption that the streak is unaffected by the Denikel is less accurate as the Denikel gets closer to that streak. On the bottom, you see that the backflow velocity trends we saw are less monotonic. So you don't really see a consistent trend going from 15 degrees to 30 degrees to 45 degrees to 85 degrees. Instead, each different angle represents the minimum peak backflow velocity along a certain range of blockage ratios. So at lowest blockage ratios, it's 15 degrees, then intermediate, it goes to 30 degrees, then 45, and then for the highest blockage ratios, 85 degrees actually gives the minimum backflow velocity. In conclusion, we've found that even a small blockage in the viscous sublayer can significantly impede reversing flow. This has given us some insight into the mechanism of shark skin at inhibiting that flow reversal. We found that blockage ratio is the primary predictor of mass flow recovery, but lower angles are also more efficient. So for a given blockage ratio, a longer denticle at a lower angle will more efficiently recover that mass flow. We also found that Reynolds number, Lang number, and Y+ have no effect. Lastly, we found that blockage ratio about 0.7 is the optimum for mass flow recovery in a Coué flow such as this with a Strasser number of 1. Because flow separation has such wide-reaching impacts, we're excited to be able to continue this research in a couple of future efforts. First, we're repeating this study with a wider range of geometries tested over all values of Strasser number, rather than splitting it into one parameterization of fluid properties and a few geometries and another wider of geometries. Because we've realized that Reynolds number, Lang number, and Y+ don't have an effect, that allows us to cover a broader range of those things that we know do have an effect. Second, we're working on a numerical counterpart to Lang et al.'s rotating cylinder shark skin experiment, from which we hope to gain a better view at sort of the larger scale effects of shark scales. Thank you.